The Humanoid 100, Mapping the Humanoid Robot Value Chain. The physical embodiment of AI touches a $60 trillion TAM, global GDP, and the meaning of work. Morgan Stanley presents the Humanoid 100, a global mapping of equities across a range of sectors and regions that may have an important role in bringing robots from the lab to your living room. As Gen AI continues to migrate from the digital world, bits, bytes, to the physical world, atoms or photons, investors are beginning to grasp the enormity of the potential disruption while struggling with paths to expression on the theme. In our original Humanoid Blue paper, we introduced the Humanoid 66, a list of both enablers and beneficiaries that we believed were most exposed at the time. Since then, commercial developments evolved at a rapid pace, especially in China, with many new players announcing their involvement or intentions to become involved. Investor interest seemed to accelerate meaningfully following NVIDIA CEO Jensen Huang's 2025 CES presentation, where he devoted roughly 40 minutes to the topic of physical AI and robotics. We are now fielding questions daily from a broad scope of global investors on how to play the embodied AI theme across a number of angles. Morgan Stanley has worked across dozens of sector teams to help our clients map differing stock expressions that are exposed to one of the most rapidly developing verticals of embodied AI. We do not pretend to present the Humanoid 100 as an exhaustive list, but rather a starting point in a conversation that will last many years and is sure to follow some exciting and unpredictable chapters along the way. We invite our clients to challenge our list and offer their own ideas of what should or should not be included as they become ever smarter on the humanoid theme and its adjacencies. Exhibit 1, Time Series of Company Transcripts mentioning humanoid. Exhibit 2, Time Series of News and Media Reports mentioning humanoid. Introducing the Humanoid 100 Stock List, our mapping of the humanoid value chain. The Humanoid 100 is the product of collaboration across Morgan Stanley's global equity research team to create a list of public companies exposed to the humanoid robot theme. Based on feedback from investors over the past 6 to 9 months, we focused more on the first derivative enablers that we believe will be consequential in building, training, and integrating a humanoid robot ecosystem. We compiled the list through a mix of discussions with our global team of analysts and conversations with subject matter experts on critical technologies and key players, supplemented by our own proprietary research to find the most exposed names globally. We then divided the companies into brain, semis, software, body, industrial components, and integrators, developing full humanoids. For every company included in the Humanoid 100, we include details on size, stock liquidity, core business competencies, rationale for inclusion, and current humanoid involvement if applicable. Currently, 52% of companies are reported to be currently involved in humanoids, and the remaining 48% are either close competitors of companies known to be involved or ones that our analysts believe have material potential to eventually be involved. For a copy of the underlying Humanoid 100 database or our US-Chinese humanoid TAM models, please reach out to your Morgan Stanley representative. Note, this is a constantly evolving space with an expansive list of hundreds of global companies involved or with reasonable potential to be involved in humanoids. There is a large subset of companies we chose to exclude due to either small size, limited current potential involvement, or lack of materiality. However, we expect there to be continued debate on which names and sub-industries may be better positioned on this theme over time. We look forward to a spirited debate and welcome all feedback. Exhibit 3, Introducing the Humanoid 100, Morgan Stanley's list of global humanoid enablers. One of our goals with the Humanoid 100 is to give investors an accurate view of the current composition of the humanoid value chain. Investors will notice that 73% of the companies confirmed to be involved in humanoids and 77% of integrators are based out of Asia, 56% per 45% out of China, respectively. A common refrain we hear from investors is the lack of Western firms to add to their humanoid portfolio outside of Tesla and NVIDIA. In our view, this is important information in and of itself as it represents the reality of the current humanoid ecosystem, which we expect may need to change materially over time. See the West's current experience with EVs, which has significant supply chain overlap with humanoids. Our research suggests China continues to show the most impressive progress in humanoid robotics, where startups are benefiting from established supply chains, local adoption opportunities, and strong degrees of national government support. Exhibit 4, 52% of companies in the Humanoid 100 have been reported to be involved in the humanoid value chain. The remaining 48% have not been reported, but we believe there is material potential for these companies to eventually be involved, if they are not already. Dissecting the humanoid anatomy. To make sense of the list and properly construct a portfolio, we believe investors need at least a cursory understanding of the makeup of the humanoid brain and body. The brain is composed of a mix of semiconductors and software, the most relevant being the foundational Gen AI models for autonomy and simulation models, digital twins for training. The body is primarily composed of sensors, cameras, lidar, force, torque, magnetic, etc., actuators, composed of motors, encoders, bearings, screws, and reducers, a web of wires and connectors, and a lithium-ion battery generally mounted in the center of the chest. The exterior is generally composed of a mix of aluminum alloys and plastics to minimize weight. For more technical details of any particular humanoid part, common engineering architectures, and the current technical barriers to manufacturing humanoids, see the Anatomy of a Humanoid section from our China Industrial Analyst, Shengzhong. Exhibit 5, Flow Diagram of a Humanoid Robot, Understanding the Interconnections between Various Components and the General Role. In the remainder of this report, we outline the contents of the Humanoid 100, review the humanoid investment case, dissect the anatomy of a humanoid, outline the latest on humanoid development progress, and review our humanoid TAM models. Humanoid 100 covering analysts. Exhibit 7, Humanoid 100 by Morgan Stanley covering analyst. To discuss a specific company on the list, please reach out to your Morgan Stanley representative or the relevant analyst below. Mapping the value chain Humanoid 100. The Humanoid 100 is Morgan Stanley's list of public companies currently involved in or otherwise materially exposed to the humanoid market. We compiled the list through a mix of discussions with our global team of analysts, conversations with clients on their preferred names to play, and our own proprietary research to find names that are involved in the value chain. We then divided the names into brain, semis, software, body, industrial components, and integrators, developing full humanoids. For every name in the Humanoid 100, we include details on size, liquidity, core business competences, rationale for inclusion, and current humanoid involvement if applicable. Currently, 52% of companies are reported to be currently involved in humanoids already, and the remaining 48% are either close competitors of companies known to be involved or ones that our analysts believe have material potential to eventually be involved. For a copy of the underlying Humanoid 100 database, please reach out to your Morgan Stanley representative. Exhibit 8, Introducing the Humanoid 100, Morgan Stanley's list of global humanoid enablers. Exhibit 9, Flow Diagram of a Humanoid Robot, Understanding the Interconnections between Various Components and Humanoid Brain, 22 companies. Companies in the brain category supply either the semis or the software AI models necessary to enable humanoid autonomy, including both training and inference. Foundational models. These are companies building the Gen AI models critical to enabling robotic autonomy. Through extensive training on vast sets of real and simulated robotic data, these models allow humanoids to understand natural language, learn from and imitate human action, and perceive their dynamic environments. The most well-known is NVIDIA's Project GR00T. Companies in the Humanoid 100, Alphabet GOOGL, Baidu, Baidu, Meta, Microsoft MSFT, NVIDIA NVDA. Data Science and Analytics. These are companies developing software that allow robotics developers and users to capture and analyze the extensive amounts of sensor data captured at the edge. Companies in the Humanoid 100, Oracle ORCL, Palantir, PLTR. Simulation and Vision Software. Simulation is critical to training robotic models, allowing robots to learn their environments and use cases prior to deployment. These companies develop a range of digital twin or vision data capture technology used in robotic humanoid training. Companies in the Humanoid 100, Alphabet GOOGL, Dassault Systems, DSYFR, Hexagon, Hexa.bse, Meta, NVIDIA NVDA, Siemens, SIEDE. Vision and Compute Semis. These are the companies producing semiconductors that are the core of the robot brain, allowing robots to learn from, perceive, and/or interact with their environments. Vision-focused semis lie at the edge and allow robots to visualize their environments. Compute-focused semis exist either at the edge for real-time AI processing or at a data center to train foundational models or build simulations. Companies in the Humanoid 100, Ambarella, AMBA, Horizon Robotics, 9660HK, Intel INTC, Mobileye, MBLY, NVIDIA NVDA, Qualcomm QCOM. Memory. These companies produce memory, DRAM, NAND, etc., necessary in all computing, likely to become more relevant in robotics with further AI penetration. Companies in Humanoid 100, Micron, MU, SK Hynix, 000660KR, Samsung Electronics, 005930KR. Semi-designers. These are silicon design firms that could benefit from a wave of new humanoid-specific semiconductor development. Companies in the Humanoid 100, ARM Holdings, ARM, Cadence Design Systems, CDNS, Synopsys, SNPS. Semi-fabrication. The actual manufacturers of semiconductors, the largest of which is TSMC. Companies in the Humanoid 100, Intel INTC, Samsung Electronics, 005930KR, TSMC, TSM. Exhibit 10, Dissecting the Humanoid Brain. Exhibit 11, Humanoid Brain Companies. Exhibit 12, Rationale for Inclusion and Current Humanoid Involvement of Brain Companies. Humanoid Body, 64 companies. Companies in the body category supply components enabling humanoid locomotion, electrical distribution, sensing, or structure. Actuator parts. Actuators are mechanical devices that convert electrical energy into motion, either linear or rotary. The greater the degrees of freedom, DUF, required, the more actuators are needed. Humanoids currently in development are generally capable of between 16 and 60 DUF. Optimus Gen 2, in particular, uses 50 DUF, driven by 28 actuators, 14 linear, 14 rotary. The latest Optimus hand, likely for Gen 3, features 22 DUF versus 27 DUF in the human hand. Future humanoids will likely have greater and greater DUF over time. Humanoid companies will often design their own proprietary actuators tailored to the specific robot, but will source various components from a web of global suppliers, similar to how automotive companies often design the vehicle architecture but outsource manufacturing to various auto suppliers. We outline the primary components below. Bearings. Bearings are key to reducing friction in a moving system while maintaining rotary precision. Humanoids use a variety of bearing types, including ball bearings, roller bearings, and needle bearings. Degree companies in the Humanoid 100, NSK, 6471JP, RBC Bearings, RBC, Regal Rexnord, RX, Skifler, SHA0DE, Timken, TKR. Screws. Screws are components that convert rotational motion from a motor to linear motion, and thus are a critical component in linear actuators. Currently, both ball and planetary roller screws are used for humanoids, but this is largely due to the limited supply and cost of planetary roller screws. Over time, planetary roller screws should represent the majority of screws used in humanoids. Degree companies in the Humanoid 100, Hungley, 601100CN, Highwin, 204090W, NSK, 6471JP, SKF, SKF.BSE, Shanghai Beatty, 603009CN, THK, 6481JP. Gearing and reducers. Reducers, as the name implies, reduce motor speed using various gear wheels to improve torque output and precision. They are a critical component in rotary actuators. Current humanoid designs use either harmonic or planetary reducers. Degree companies in the Humanoid 100, Harmonic Drive System, 6324JP, Highwin, 204090W, Hota, 153060W, Leader Drive, 688017CN, Naptesco, 6268JP. Regal Rexnord, RX, Shuanghuan, 002472CN, Timken, TKR, Zhongda Leader, 002896CN. Motors and rare earth magnets. Electric motors convert electricity into mechanical energy and are used in all electric actuators. Most motors create motion using rare earth magnets that repel against electrified coils of wire, creating a rotational effect. Humanoids generally use either frameless torque motors, lower technical barriers, or coreless motors, greater technical barriers. Degree motor companies in Humanoid 100, Eston, 002747CN, Leadshine, 002979CN, Moons Electric, 603728CN, Nidec, 6594JP, Regal Rexnord, RX, Sensata, ST, Shenzhen Innovance, 300124CN, Jiawei, 003021CN. Zhongda Leader, 002896CN. Degree rare earth magnet companies in Humanoid 100, JLMAC, 6680HK, Liners Rare Earths, LYCAU, MP Materials, MPUS, Northern Rare Earth, 600111CN. Encoders. Encoders are sensory devices that are fitted on and monitor the speed and output of a motor, sending back a signal to control variables such as position, speed, and torque. Degree companies in the humanoid 100, Nidec, 6594JP, Novanta, NOVT, Sensata, ST. Sensors. Humanoids are outfitted with a wide array of sensors to allow humanoids to perceive their environment and collect necessary data. We outline the primary types below. Cameras and vision sensors. Captures full images, cameras, or light properties to enable humanoid perception. Degree companies in the humanoid 100, Analog Devices, ADI, Hexagon, Hexa.bse, Intel INTC, Keyence, 6861JP, Onsemi, ON, RoboSense, 2498HK, Sony Group, Sony, T Connectivity, TEL, Teledyne Technologies, TDY, Will. Semiconductor, 603501CN. A radar and LiDAR enables depth perception through radio waves, radar, or lasers, LiDAR, to detect objects and measure distances. Degree companies in the humanoid 100, Aptiv, APTV, Intel INTC, Magna, MGA, RobotSense, 2498HK, Teledyne Technologies, TDY, Valeo, FRFR. A magnetic detects presence of a magnetic field. Generally in humanoid hands and allows the robot to sense if it is touching something. Degree companies in the humanoid 100, Allegro Microsystems, ALGM, Melexis, MeleBE. A force and torque. Force sensors allow the humanoid to detect and measure weight and pressure. Torque sensors allow humanoids to assess the torque applied to its actuators. Degree companies in the humanoid 100, Kelly Sensing, 603662CN, Novanta, NOVT, Sensata, ST, T Connectivity, TEL. Batteries. Humanoids generally use a battery pack made of cylindrical lithium-ion cells contained within the torso of the robot. Companies in the humanoid 100, CATL, 300750CN, EVE Energy, 300014CN, LG Energy Solution, 373220KR, Samsung SDI, 096770KR. Analog semis. Work with sensors to help regulate temperature, speed, position, electrical distribution, etc. Many sensors are technically a type of analog semi. Companies in humanoid 100, Allegro Microsystems, ALGM, Infineon, IFXDE, Melexis, MeleBE, NXP, NXPI, Onsemi, ON, Renesas, 6723JP, ST Micro, STM, Texas Instruments, TXN, Will Semiconductor, 603501CN. Body, wiring, thermal. The structure of the robot and method of power distribution and cooling. Companies in humanoid 100, Amphenol, APH, Aptiv, APTV, Magna, MGA, T Connectivity, TEL, Shushing, 603305CN, Sanhua, 002050CN, Tuopu, 601689CN. Diversified automation companies. These are companies that provide a wide range of automation robotics-related solutions such that they were best left in their own category. Potential to supply most necessary components given scale and expertise if there is sufficient demand. Companies in humanoid 100, Hun High Precision, Foxconn, 2317TW, Honeywell, HON, Rockwell Automation, ROK, Siemens, SIEDE. Exhibit 13. Dissecting the humanoid body. Exhibit 14. Humanoid body companies. Exhibit 15. Rationale for inclusion and current humanoid involvement of body companies. Humanoid integrators, 22 companies. Integrators are companies currently building full humanoid robots or that have the reasonable potential to do so given their expertise in manufacturing other robotics or automation platforms. Most of these companies are larger, mature corporates that also have in-house robotics businesses. We note the vast majority of younger humanoid startups are currently private. We group the integrators below. Autos. There are a number of automotive companies currently developing humanoids, likely due to the engineering and manufacturing overlap combined with potential in-house use cases to reduce labor intensity and improve margins over time. Companies in humanoid 100, BYD, 002594CN, GAC Group, 2238HK, Hyundai Boston Dynamics, 005380KR, Tesla TSLA, Toyota, 7203JP, Speng, XPEV. Consumer electronics. Similar to automotive companies, these firms likely manufacture, or may manufacture, robots due to their expertise in scale manufacturing and ability to develop electronic architectures for robots using in-house talent. A number of these companies may see humanoids as an extension of household electronics and leverage humanoids as another method to penetrate the home. Companies in Humanoid 100, Apple AAPL, Hun High Precision Foxconn, 2317, TW, LG Electronics, 066570.HK, Samsung Electronics, 005930KR, Sony Group, Sony, Xiaomi, 1810HK. E-commerce and Internet. These companies would likely benefit from overlap between humanoid design and their existing technical expertise, and additionally could have in-house use cases to reduce costs over time. The companies in Humanoid 100, Alibaba BABA, Amazon AMZN, Naver, 035420, KR, Tencent, 700HK. Legacy robotics companies. These are legacy cobot manufacturers that have existed for decades but have the potential to eventually develop humanoids if they are not already doing so. The companies in Humanoid 100, ABB, ABBNCH, Midea Ikuka, 000333CN, Teradyne, TER. Humanoid near pure plays. These are young humanoid developers that are the closest to humanoid pure plays out of any company on this list. Exhibit 16, Humanoid Integrators. Exhibit 17, Rationale for Inclusion and Current Humanoid Involvement of Integrators. Humanoid 100 Composition. Exhibit 18, 52% of companies in the Humanoid 100 have already been reported to be involved in the humanoid value chain. The remaining 48% have not been reported, but we believe there is material potential for these companies to eventually be involved, if they are not already. Exhibit 19, Humanoid 100 Brain-Body Integrator Composition by Region. Exhibit 20, Humanoid 100 Regional Composition by Major Category. Thematics AI Mapping Survey. Our Thematics team conducted a survey in June 2024 incorporating results from Morgan Stanley Global Research Analysts to map out both the type and degree of AI exposure for all covered names. In the process of putting together our Humanoid 100, we cross-referenced with the AI mapping survey results. We'd note that more than half, 58%, of our Humanoid 100 are reported as either enablers in some form, either an enabler or enabler adopter. For materiality, the vast majority, 65%, of our list has at least moderate exposure, with 25% classified as at least significant, and 19% as core to thesis. Exhibit 21. Analysts surveyed AI exposure of companies in the Humanoid 100. Exhibit 22. Analysts surveyed AI materiality of companies in the Humanoid 100. Exhibit 23. Analysts surveyed pricing power of companies in the Humanoid 100. Exhibit 24. PE rank of Humanoid 100, cons. Exhibit 25. PE versus consensus 3 years revenue CAGR, full. Exhibit 26. PE versus consensus 3 years revenue CAGR, excluding outliers. Exhibit 27, LTM performance of Humanoid 100 versus the S&P 500. Exhibit 28, LTM performance of brain companies in the Humanoid 100 versus the S&P 500. Exhibit 29, LTM performance of body companies in the Humanoid 100 versus the S&P 500. Exhibit 30, LTM performance of integrator companies in the Humanoid 100 versus the S&P 500. Exhibit 31, LTM performance of US and Canadian companies in the Humanoid 100 versus the S&P 500. Exhibit 32, LTM performance of China and Taiwanese companies. Exhibit 33, LTM performance of other APAC companies in the Humanoid 100 versus the Nikkei 225 and Kospi Composite. Exhibit 34, LTM performance of EMEA companies in the Humanoid 100 versus the DAX Composite and FTSE 100. The Humanoid Investment Case. The below is an excerpt from our Humanoids Blue Paper. 4 years, machine learning was limited to self-reinforcing software algorithms. The advancement of large language models, LLMs, and Gen AI have made a great leap into the field of robotics, accelerating how physical machines learn, through natural language, imitation, and simulation. Gen AI is transforming how robots learn by giving them a chance to observe and imitate behaviors in both the physical and virtual world, connected through natural language and iterated in the data center. Similar to how large language models, LLM, help drive ever greater capability of ChatGPT, multimodal models, MMM, are driving innovation in robotics. AI algorithms can significantly shorten the R&D cycle by automating repetitive tasks, enhancing data analysis and predictive capabilities, enabling virtual simulation, and optimizing design and testing processes. As an AI-adjacent field, humanoid hardware development can now directly benefit from the increased capital formation and R&D investment into the robotics theme. AI leaps into the physical or atomic world. AI is all around us. AI listens to you. AI sees your face and body. AI knows where you are right now. AI can read. AI can write. AI can talk. AI can make a picture of cats wearing little cowboy hats playing canasta. But other than running loads of algos and activating a few switches, AI rarely ever actually moves. In nature, motility is an organism's ability to move independently under its own energy. According to fossil records, the earliest evidence of motility on Earth traces back to bacterial flagella, spindle-like extensions used for locomotion, in the Precambrian era. The lines between mobile device and robot are beginning to blur. Exhibit 35, Top Humanoids from Pop Culture. Why humanoids? Many investors reading this report will ask the question, why do we need robots shaped like humans? There are indeed strong arguments for robotics to take many highly specialized forms: robot arms, snake-shaped robots, robot dogs, robotic dust, and as many form factors as you can imagine. However, many robot and AI experts say the strongest argument for robots in a human form factor is that in a world already created for humans, the environment is already brownfield for humanoids. NVIDIA CEO Jensen Huang recently stated, "The easiest robot to adapt into the world are humanoid robots because we built the world for us. We also have the most amount of data to train these robots than other types of robots because we have the same physique." Additionally, think of the great variety of tasks that humans are able to perform with our bare hands or using tools and the multitude of machines designed for human hands and fingers. Exhibit 36, Pros and Cons of Humanoids versus Specialized Robotics. Framing the TAM. As of November 2023, the U.S. labor force stands at around 162 million people. At an average salary of $59,428, the U.S. labor market is worth just shy of $10 trillion annually. According to Statista, there are approximately 3.4 billion people employed worldwide. Assuming a $9,000 per worker annual salary implies approximately a $30 trillion global labor market, roughly 30% of global GDP. Given the thousands of individual jobs performed by humans, the TAM exercise required a far more detailed analysis across job stratification to understand the path of humanoid substitution gated by economic paybacks, supporting supply chain infrastructure, and other factors. As such, we built a proprietary Morgan Stanley humanoid TAM model to address a more realistically available subset within the theoretical $30 trillion universe over time. In our US TAM model, we forecast a humanoid population, cumulative installed base, of 8 million units by 2040, $357 billion wage impact, and 63 million units by 2050, $3 trillion wage impact. While our analysis does not currently consider a humanoid installed base greater than the existing human labor pool, there are scenarios where the economic benefits of the technology could make this a reality. At his most recent AGM, Tesla CEO Elon Musk expressed his belief that humanoids will eventually outnumber humans by 2 to 1 or more. I think the ratio of humanoid robots to humans will probably be at least 2 to 1, something like that. 1 to 1 for sure. So, which means like somewhere on the order of 10 billion humanoid robots. Maybe 20 billion or 30 billion. Exhibit 37, Cumulative Number of U.S. Jobs with Humanoid Optionality, 2028 to 50, MN. Exhibit 38, Cumulative U.S. Wage Impact, 2028 to 50, $BN. 1 billion humanoid robots by the 2040s? Tesla CEO Elon Musk has been increasingly focused on Optimus, Palo Alto Engineering Center, in recent months, per his comments. Tesla first unveiled its humanoid robot, Optimus, on September 30, 2022. The bipedal robot included 28 actuators in 2 categories. 1. Rotary actuators, consisting of harmonic reducers, ball bearings and sensors, for rotating motion such as shoulders and elbows. 2. Linear actuators, comprising planetary rollers, ball bearings and sensors for linear motions like human muscles. 12 actuators for 2 hands. Many more details have been kept internally at the company. In January of this year, Elon Musk said he expected to see over 1 billion humanoid robots in operation by the 2040s. At Tesla's June 13, 2024 annual shareholder meeting, Mr. Musk stated he expects to have at least 1,000 Optimus robots working at Tesla next year, and that things are gonna scale up very rapidly from there. In the same meeting, Mr. Musk expressed his confidence that humanoid robots will eventually outnumber human beings and probably be 20 billion or more, no timeline shared. A dynamic, fast-changing competitive landscape. Beyond Tesla, dozens of startups and established firms have engaged in humanoid robotics development on the back of the rapid growth of Gen AI in 2022-2023. We note even before NVIDIA's keynote speech in March 2024, which left little to the imagination about the company's intentions for physical AI, robotics were a recurring AI theme, including at the Morgan Stanley TMT conference last March. After a number of false starts, an array of venture investors and companies across are betting on the promise of embodied AI. Humanoid startups Figure AI and Agility Robotics were valued at $2.6 billion and $1.2 billion, respectively, in private funding rounds last year, with the broader theme attracting major investors including OpenAI, SoftBank, Tiger Global, Amazon, NVIDIA, and Microsoft among others. Additionally, major public companies, across industries ranging from automotive to consumer electronics, are actively involved in humanoid development, while others are actively partnered with humanoid startups to explore potential future use cases. Exhibit 39, Selection of Private Humanoid Companies Startups. Exhibit 40, Selection of public companies involved in humanoid development or exploring implementing humanoids in the workplace. Robotics having a ChatGPT moment. According to Vincent Van Hook, Senior Director for Robotics at Google DeepMind, experts in the robotics community refer to 2 years ago as the good old days, as he explains how LLMs and Gen AI have very abruptly flung the field of robotics from an isolated robot island firmly onto the AI flywheel. The science of LLM, large language models, and generative AI had long been seen as completely separate from the world of robotics, actuation. These worlds are colliding and the impacts are profound. We've been here before. In 1821, Michael Faraday ran an electric current through a wire suspended over a magnet in a glass, observing the rotation of the wire. This marked not only the discovery of how electrical energy can create mechanical movement, the first electric motor, but it also connected two areas of science that until then seemed unrelated, electricity and magnetism. Albert Einstein found connections between the properties of physical matter and light that were previously never conceived, E=mc². Might we be on the verge of unlocking the relationship between Gen AI and robotics? Exhibit 41, Seemingly unrelated areas of science can combine with profound effect. Exhibit 42, Public company documents and transcripts mentioning humanoid. Exhibit 43, News reports mentioning humanoid. Cybernetic collective robotic learning. Imagine for a moment a humanoid robot standing in front of a kitchen island on which an onion sits on a small plate next to a paring knife. Now imagine a large warehouse with 1,000 humanoid robots each standing next to a kitchen island with the onion on a plate next to a knife. As each trial and error accumulates among the group, the entire population learns at the collective rate of the best robot at any point in time. The aggregated learning of the cybernetic collective spools up, to achieve an accelerated frontier of group learning. When the physical practice is completed with a winning robot having peeled its onion better than the other 999, best practices can then be shared and further improved through hundreds of millions of trials among their digital twins in a simulated omniverse. Exhibit 44, with NVIDIA Project GR00T, humanoid robots train in a simulated version of reality called Omniverse. The below image shows digital. Have you seen or interacted with a robot today? Some of you may have. Most of you reading this at the beginning of 2025 likely have not. This rather nostalgic period of human technological history is quickly passing. The ongoing LLM Gen AI revolution is in the early days of crossing over into robotics. LLM and robotics were long seen as vastly different areas of science. But there may be far more overlap in how the advancement of LLM accelerates the training and learning of the robot, whether it is a car-shaped robot or a human-shaped one. The AI brain is searching for its robot body. Humanoid versus autonomous cars. Autonomous vehicles, AVS, are robots. Rather simple robots, in the form factor of a car. By simple, we mean there are only 3 primary actuation outputs of a robotaxi. 1. Steering wheel, 2. Accelerator pedal angle and 3. Brake pedal. However, the operating domain is extremely complex, public roads riddled with unpredictable elements. We believe that the humanoid time to commercialization will materialize faster than AVS given the variability of the AV operating environment, real world, and corresponding safety implications, human passengers, pedestrians, versus the humanoid form factor, which can learn in a geofenced domain, warehouse, factory closed work cells. Even though humanoids have more physical outputs, the difficult operating domain, safety concerns, and regulatory scrutiny that autonomous vehicles face pushes their adoption curve out to the right in our view. Key drivers of humanoid adoption. The story of humanoid robotics involves an understanding of three primary domains: AI, robots, and people. At various stages, advancements in AI, multimodal models, neural net training, compute, may progress faster than the physical science of robotics, i.e., optics, actuation, battery, manufacturing, which may march along its own path of potentially nonlinear improvement. All the while, a number of drivers of labor factors across industries and regions will significantly determine economic payback periods, adoption rates, and social acceptance. Exhibit 45. Labor availability versus AI and robotics acceleration. While advanced humanoid development remains in its early stages, we believe the path of progress over the past few years in the adjacent areas of 1. Gen AI, 2. Actuators and mechanics, and 3. Battery storage are proving to be significant contributors to humanoid development. Further advancements in these three areas will be key to achieving humanoid commercialization. Exhibit 46. As contributing technologies have advanced over the past decade, intelligent humanoid development has continually increased in relevance. A number of gating factors must also be considered. Widespread commercialization of humanoid robots at scale must overcome a host of technological challenges as well as a wide range of societal, policy, safety impediments along the way. On the tech side, creating humanoids able to navigate the nuances and complexities of human environments will likely require continued advancements in Gen AI as well as efforts to tailor these advanced models specifically for humanoids. Additionally, further refinement of precision actuators, sensors, and battery capacity will be critical to improving the scope of tasks that can be executed by humanoids. Despite decades of modern robotics development, the sudden and rapid rise of Gen AI models may create scenarios where the mental capabilities of humanoids surpass the physical capabilities, opening the door to a range of potential hardware bottlenecks that will need to be addressed as humanoids become exponentially smarter. The social, policy, safety considerations as they relate to AVS helps us understand the range of potential hurdles for humanoids. However, we believe the ability to train humanoids using digital twins or in closed-off, geofenced work cells, as opposed to public streets, gives humanoids a relative advantage in approaching potential safety regulations. Exhibit 47. Potential hurdles to humanoid adoption. Leveraging the Morgan Stanley Asia Industrials Cortex, we assess the humanoid bill of materials, BOM, and map the key enablers within the humanoid supply chain. From China Industrials, Shenzhong, to Japan Industrials, Lisa Jiang, and China Auto Suppliers, Shelley Wang, we dive into the inner workings of a humanoid, breaking down component costs and the potential for future cost reduction. Per our estimates, building humanoid robots could range from $10,000 to $300,000 depending upon configuration and downstream application. For example, per primary component supplier price quotes and proprietary analyses, we estimate Tesla Optimus Gen 2's current BOM is $50,000 to $60,000 per unit, ex software. However, with the benefit of scale, the introduction of AI algorithms to significantly shorten the R&D cycle, and the utilization of cost-effective components from China, we see opportunities for significant cost reduction to achieve CEO Elon Musk's targeted Optimus selling price of $20K. Exhibit 48. We estimate current total X software BOM for Tesla Optimus at $50,000 to $60,000 per unit. Anatomy of a humanoid. The below is an excerpt from our Humanoids Blue Paper. What goes into a humanoid robot? Shenzhong China Industrials. As the embodiment of AI, humanoid robots are designed to think and act like humans. AI enables robotic brain function, underpinning the robot's intelligence level and the range of potential use cases. Mechanical parts enable the body function, underpin manipulation, and the BOM reduction potential. We believe future AI plus machinery improvement will decide the pace of humanoid adoption. The operating system, AI plus motion control system, is the most valuable part of a humanoid robot since it underpins the humanoid's intelligence level, including multimodal perception, logical thinking, and motion control. The AI chip, mostly provided by AI chip players such as NVIDIA, though we note Tesla reuses its autopilot algorithm for Optimus, perceives input information and generates instructions after logical thinking. The motion control system, which receives the instructions from the AI chip, controls the joints to perform commands sent from the AI chip with high precision and stability, and also, in return, provides real-time feedback to the AI chip. AI algorithms can empower the humanoid's operating system mainly by improving scalability, precision, and stability. In the long term, OEMs with the leading operating systems could drive both the direction of humanoid technological advancement and the pace of humanoid mass production. Currently, humanoid AI algorithms are still in the beginning stages of development, requiring lots of on-site validations, algorithm iterations, and hardware run-in for perfection. We believe AI algorithms can empower the humanoid operating system by improving its scalability. The humanoid operating system, integrated by humanoid OEMs, is usually specifically designed for a model or series in different scenarios. AI algorithms can improve versatility of the operating system, thus accelerating penetration of humanoid robots in different downstream applications. Precision, AI algorithms can effectively improve motion control precision with real-time monitoring capabilities, autonomous learning and task optimization, and unsupervised simulation and testing. Stability. Integrated with a variety of high-precision sensors, AI algorithms can improve the humanoid operating system stability with processing massive multidimensional sensor data, providing more granular data analysis, and indicating potential failures by early identification of anomalies. Humanoid actuators are core to performing human-like motions, acting as the robotic equivalent to human joints or muscles. Over time, humanoids will need greater amounts of actuators to facilitate greater degrees of freedom. Hardware plans can significantly vary across different humanoids in terms of degrees of freedom, DoF, hands design, sensor sensitivity, etc. We include an overview of notable humanoid hardware below. The bot brain, or central computer, is a system-on-chip, SoC, that processes the wide array of inputs and outputs used to drive all the hardware used on the robot, cameras, Wi-Fi module, audio, etc. For Tesla, the design for the bot brain is largely derived from Tesla FSD hardware and software. The humanoid body is mainly composed of actuators and supporting systems, battery pack, structural parts, thermal system, etc. Degree actuators are devices that enable motion in a system, both rotational or linear, similar to human joints. The greater the degrees of freedom required, the more actuators that are needed. Currently, humanoids in development generally are capable of between 16 and 60 DoF. Optimus Gen 2, in particular, uses 50 DoF, driven by 28 actuators, 14 linear, 14 rotary. The actuators themselves are comprised of a combination of screws, reducers, motors, sensors, ball bearings, and encoders. Degree structural parts are supporting material around the humanoid body, such as the skeleton and outer shell. The Optimus Gen 2 loses 10 kilograms without sacrificing its structure and performance, primarily from the use of lightweight materials such as PEEK, polyether ether keton, and high power density actuators. PEEK is a synthetic material often used as a metal substitute due to its excellent strength and light weight, which helps to reduce overall energy consumption while preserving performance. Exhibit 49, linear and rotary actuators are comprised of screws, reducers, motors, sensors, bearings, and encoders. Exhibit 50, overview of key parts used in a humanoid robot. Exhibit 51, humanoid motion can be driven by electric, hydraulic or pneumatic drive system, but electric-driven designs. Exhibit 52, hardware design of selected humanoid models. A worldwide supply chain. Shenzhong, China Industrials. Screws, motors, reducers, and sensors are the key components in machinery manufacturing. While the high-end component markets are dominated by Europe, US and Japan companies, Chinese companies are competitive in lower mid-range products where they aim to provide valuable products. However, there is still a large gap between the lower mid-range versus high-end products in terms of precision, stability, payload, and production process optimization capabilities. Screws are components that convert rotary motion and linear motion into one another. They are widely used in CNC machine tools, manufacturing equipment, robots, precision instruments, and other downstream applications. Humanoids, such as Tesla Optimus, mainly use ball screws and planetary roller screws for linear actuators to perform high-precision motions. However, these components have high barriers to entry and expensive production equipment and raw materials. Today, high-end screw manufacturing is dominated by Europe, Rolvis, SKF, etc., and Japanese companies, NSK, etc. There is also still a wide gap in efficiency, payload, and precision between high-end Western and Japanese producers and Chinese companies. However, some Chinese companies, Hongli, Best, etc., have started to penetrate the high-end market and have proceeded to demo validation for humanoid OEMs. Motors are used to generate driving torque and are mounted on the humanoid joints to control motion. On humanoids, frameless torque motors are widely used for both linear and rotary actuators to facilitate manipulation due to their small size, compact structure, light weight, small rotating inertia, and low starting voltage. Coreless motors are generally used in human-like hands, featuring higher energy saving, low voice, high useful life, and high torque. Frameless torque motors have a relatively low technology barrier. Germany's Kohlmorgen, private, dominates in high-end frameless torque motor for high-end applications, while Chinese products are widely used for other lower mid-range applications. Kingco, not covered, is the leading Chinese supplier and one of few that can provide high-quality frameless torque motors. On the other hand, coreless motors have a much higher technology barrier, with concentrated applications in medical and military equipment, drones, etc. Currently, foreign suppliers account for greater than 85% market share in China. Chinese companies entered the market in the 2010s, but there is still a large performance gap between domestic and imported products on no-load speed and rated torque. However, we note that for coreless motors used on humanoid hands, Chinese companies such as Moons have already penetrated the humanoid supply chain and are running demo validation for OEMs. Reducers are used both for reducing motor speed and for improving the torque output and motion accuracy of humanoid joints. Planetary reducers, harmonic reducers, and RV reducers are the three primary categories of reducers. Different humanoid design require different type or quantity of reducers. All three of these primary reducer categories are dominated by Japanese companies, Harmonic Drive, Shimpo, subsidiary of Nidec, Naptesco, etc. Today, Chinese companies still have a large performance disadvantage on both precision and stability. However, we note that leading Chinese players, such as Leader Drive, have sent harmonic reducers for demo humanoids. Sensors, including vision sensors, force sensors, inertial sensors, temperature sensors, etc., are the essential hardware for humanoids' multimodal perception both internally, perception of its own position, and externally, perception of touch, vision, hearing, etc. Force sensors are more vital sensors for humanoids to achieve smooth and real-time force adjustments under various scenarios. 6-axis force sensors, the most complex force sensors, can measure payloads from any direction and bear payloads 5-20x higher than rated measurement ranges. ATI, a subsidiary of Novanta, NOVT not covered, is the inventor of the 6-axis force sensor and dominates the market, while most Chinese companies still lag without long-term accumulation in sensor calibration and decoupling. Other first movers such as Kunwei, private, and Sunrise Instruments, private, have begun to penetrate the sensor supply chain for humanoids. Assessing the humanoid bill of materials. There is a wide range of potential BOM costs for humanoids, largely depending on design complexity, material, and market positioning. Under our estimates, building humanoid robots could range from $10,000 to $300,000 given different configuration and downstream application requirements. For instance, China's Unitree announced its G1 humanoid would be priced at $16K with a simplified algorithm module, halved degrees of freedom, lack of linear actuators, shorter battery life, and lower carrying capacity. In contrast, with an estimated selling price at $250,000 in 2025, Agility Robotics' Digit is specifically designed for logistics, featuring a high power capacity and payload, high man-machine interaction intelligence, and a higher degree of balance or stability. Using Tesla's Optimus Gen 2 as an example, we estimate the current total X software BOM at $50,000 to $60,000 per unit, using price quotes from various component suppliers. However, we note this is using quoted prices for individual components used to create the robot. For a player building humanoids at scale, such as Tesla, the BOM could likely be significantly lower given various relationship, bundling, and/or bulk discounts with the various component suppliers. In our view, Tesla's Optimus has significant opportunity for cost reduction to achieve CEO Elon Musk's targeted selling price of $20K. We break down the BOM for Optimus Gen 2 by function. The bot brain is based on a Tesla SoC and additional outputs and inputs, e.g. Wi-Fi, camera, audio, etc. For the brain itself, we estimate the hardware cost is $2K a humanoid, 4% of total. Note, This excludes any potential software cost, e.g., FSD training costs. Our all-body motion is driven by 28 actuators, 14 linear actuators and 14 rotary actuators. The upper body, shoulder, elbow, arm, hands and waist, requires 16 actuators which we estimate could cost $26K humanoid, 47% of total, and lower body, pelvis, legs, feet, requires 12 actuators which cost $26K humanoid, 48% of total. Our other supporting systems including the battery and various structural parts cost $419 per humanoid, 0.8% of total. When breaking the components down by product type, the key 5 parts of sensors, screws, motors, reducers, bearings cost $20K, $11K, $11K, $7K, $434 per humanoid, accounting for 37%, 20%, 20%, 13%. 0.8% of the total BOM. Exhibit 53, we estimate current total X software BOM for Tesla Optimus at $50,000 to $60,000 per unit. Exhibit 54, Optimus Gen 2 BOM breakdown by parts. Exhibit 55, Optimus Gen 2 BOM breakdown by function. Tracking humanoid progress. Patent filings. Exhibit 56, monthly global patent application filings mentioning humanoid, latest data as of the 19th of November 2024. Exhibit 57, global patent filings mentioning humanoid by office over the past 5 years. Exhibit 58, top filers of U.S. patent applications mentioning humanoid over the past 5 years. Exhibit 59, public company documents and transcripts mentioning humanoid. Exhibit 60, news reports mentioning humanoid. Exhibit 61, notable humanoid unveils since 2022, blue equals USA, yellow equals China, green equals EMEA, red equals rest of Asia. Exhibit 62, humanoid unveils by year and country. Exhibit 63, humanoid unveils since 2022 by country. Exhibit 64, humanoid unveils since 2022 by primary use case. Exhibit 65, monthly China humanoid company funding activity. Overview of major humanoid robots. Exhibit 66, notable humanoids with specs, 1/2. Exhibit 67, notable humanoids with specs, 2/2. US and China humanoid TAM adoption estimates. Note, the underlying Excel file for the TAM model discussed in this section is available upon request. Please reach out to your Morgan Stanley sales representative to obtain the model. US humanoid TAM estimates. As part of our humanoid blue paper published last June, we conducted a bottom-up analysis on the US labor market to assess each occupation's humanoid ability and estimate the humanoid TAM, US only. We started by gathering all 831 US civilian occupations using the Bureau of Labor Statistics May 2023 Occupational Employment and Wage Statistics Survey. Working with our economics team, we assigned one of 4 values to measure the humanoid optionality of each occupation as follows. A strong potential, 46% of occupations. Degree: these are jobs that are predominantly unskilled and most likely to be perceived as boring, dangerous, and/or repetitive. Extremely unlikely to be performed by an AI model due to physical requirements of the job. Degree: for the purposes of our TAM model, we assume 70% of employees in these positions are substitutable with humanoids, i.e., 70% optionality factor. A moderate potential, 9% of occupations. Degree: these are jobs that are often physical in nature or which require a physical presence but are not necessarily unskilled or obviously perceived as boring, dangerous, and/or repetitive. Degree: for the purposes of our TAM model, we assume 50% of employees in these positions are substitutable with humanoids, i.e., 50% optionality factor. Lower potential, 19% of occupations. Degree: these are jobs that require complex human-to-human interaction or specialized skills not likely to be easily replicated by a robot, X. Doctors, supervisors, engineers, etc. A notable amount of these jobs are also more likely to be performed by an AI model rather than humanoid robots due to limited physical requirements. Degree: for the purposes of our TAM model, we assume 30% of employees in these positions are substitutable with humanoids, i.e., 30% optionality factor. A limited potential VNA, 26% of occupations. Degree: these are jobs that require a significant amount of complex human-to-human interaction or could more feasibly be performed by an AI model rather than a humanoid robot due to limited physical requirements. Degree: for the purposes of our TAM model, we assume none of the employees in these positions are substitutable with humanoids, i.e., 0% optionality factor. Using the humanoid substitution risk framework, we multiplied the number of employees in each occupation by the relevant humanoid optionality factor and then by the median annual wage for the given occupation. Note, this analysis is an illustrative effort to depict how humanoids could potentially be adopted in certain industries and how the TAM could be captured over time. Our timeline analysis also does not account for the possibility that the introduction of humanoids could create new sectors, expand existing sectors, or create new job opportunities for humans. For simplicity, the analysis also assumes no growth in the total size of the US labor market and its existing industries. Based on our analysis, we believe 75% of occupations and 40% of employees in the US have some degree of humanoid ability. This amounts to an estimated addressable market of $3 trillion, or 63 million humanoid units in the US alone. While this estimate considers only the US, we note that a TAM based on the global labor market could be greater by multitudes of magnitude. Exhibit 68, Humanoid Substitution and US Wage Impact by Tier, 2030 to 50. Exhibit 69, Cumulative US Humanoid Adoption, 2028 to 50, Millions of Humanoids. Exhibit 70, Cumulative US Wage Impact, 2028 to 50, $billion. Overlaying an average selling price per humanoid and a replacement rate assumption onto our units adoption analysis, we estimate the total revenue generated by the US humanoids market each year. We assume an initial average selling price per humanoid in 2028 of $150,000 each, which declines to $50,000 by 2040. Post-2040, we assume a modest price increase of 0 to 1% per year driven by inflation offset by further technological advancements. We also assume a replacement rate of 8 years per humanoid. Based on these assumptions, we estimate that the US humanoids market could generate $4 billion total revenue by 2030, $240 billion total revenue by 2040, and $1 trillion total revenue by 2050, with rapid acceleration in revenue growth occurring in 2040 to 50. Exhibit 71, US humanoids market, total revenue, $BNS. China humanoid TAM estimates. Shenzhong. We introduce our China humanoid market forecast model to assess the market potential in China, expecting the market to reach RMB 12 BN, RMB 216 BN, RMB 6 TR by 2030 E divided by 35 E divided by 40 E divided by 50 E, with volume to reach 1.5 MN, 7.4 MN, 59 MN by 2030 E divided by 35 E divided by 50 E, respectively. We factor in China's low cost of labor and massive population, estimating a lower adoptability compared to US similar industry. Also, we believe a significant price cut is critical for humanoid to become a mass market product. We anticipate the ASP and BOM to decrease at CAGR of 8% and 11%, respectively. While the incremental volume could bring meaningful growth, there is short-term margin pressure to upstream manufacturers in China. Exhibit 72, China humanoid market size, RMBBN. Exhibit 73, China New Humanoid Adoption, K-Unit. Exhibit 74, China Humanoid ASP versus BOM. Valuation Methodology and Risks. Tesla Inc., TSLA.O. Our PT of $430 is comprised of 5 components. 1. $86 per share for core Tesla auto business on 5.2mm units in 2030, 9% WACC, 14x 2030 exit EBITDA multiple, exit EBITDA margin of 16.1%. 2. Network services at $172, 65% attach rate at $200 ARPU by 2040. 3. Tesla Mobility at $90 on DCF with 7.5 MN cars at $1.46 mile by 2040. 4. Energy at $65 per share, and 5. Tesla as a third-party supplier at $17 per share. Risks to upside. Disclosure on service revs. Increased FSD attach rate. Cost milestones on new battery. New model intro, Cybertruck, Multivan, Semi. 3-road party battery win. Geographic penetration and new capacity. Risks to downside. Competition, legacy OEMs, Chinese players, big tech. Execution risk, multiple factory ramps. Market does not recognize Dojo-enabled services up, lower than expected attach rate and RPU. China risk. Dilution. Valuation.
观众朋友们好，欢迎大家来到本期的思想先驱报栏目。在之前的几期节目中我们为大家讲述了黄仁勋的童年以及少年时代。那么说到芯片这个问题今天我们暂停一下，为大家介绍美国在几十年前和一个亚洲国家的芯片大战。这个国家可不是中国，而是日本。那我们知道美国芯片最初的发展与国防部军事系统的资金投入可以说是息息相关的。但是到了这个60年代、70年代之后，之前人家讲说这个五角大楼创造硅谷，这个形式就会有了改变了。为什么呢？因为和平时代芯片行业就不再那么专注于军事生产了像英特尔这样的公司更多的是希望打开消费市场，而不是从五角大楼那里边来为导弹这样的一个我们叫做空中雷达位置信息等等等等精确打击来实施有关的野心计划。后来呢，美国的军队在越南战争中失利了，但是对于芯片行业来说，把新加坡、日本、亚洲这一些国家迅速的与美国绑定在一起，让整个世界和美国的创新基础设施可以说是紧密的绑定在了一起。但是在这样的一个时候除了大家熟知的像英特尔像德州仪器这样的美国企业，有几个日本公司也在制作 DRAM 存储芯片但是当时这一些日本公司根本不被硅谷看得上眼。是什么公司呢？今天大家一提起来大名鼎鼎，其中有一家叫做 Toshiba， 叫做东芝，还有呢就是日本电器公司NEC。 为什么呢？因为硅谷认为美国的芯片制造商是发明科技的人经营的，日本是什么呢？根据在这个芯片战争这一本书中对于当时美国硅谷巨头的描述，说日本就是咔嚓咔嚓之国。什么叫咔嚓咔嚓之国呢？就是说日本工程师经常呢带一个照相机到各种各样的这个学术会议上那么呢照相机到处照相说他们呢就是靠模仿这样的一个方式来剽窃美国的技术。也的确，当时美国有很多的芯片制造商都在这个知识产权诉讼上与日本的竞争对手对簿公堂。但是有一个硅谷的著名的企业家却发现情势不妙。他是谁呢？他是安德森。安德森是谁就是惠普公司的创始人之一他最开始也没有把这一些日本公司看在眼里，但是他测试了一下日本公司的芯片，就发现了一个惊人的事实。不知不觉中日本公司做的 DRAM 的芯片质量已经超过了美国。那么根据《芯片战争》这一本书中的介绍3家日本公司的芯片1000小时故障率是多少呢？0.02%。最差的美国芯片的故障率是多少呢？是日本芯片的10倍多。而最低的芯片故障率，就是最好的美国公司的芯片，大概故障率是日本公司的4-5倍之多。所以这个安德森就发现现在已经必须要把日本看在眼里了。那我们也知道在整个战后这个日本制造就像曾经的这个中国制造一样，被认为是廉价的代名词。后来索尼出了一个企业家叫做盛田昭夫。这个盛田昭夫最开始呢这个到美国、到法国、到欧洲被人看不起，说这个人根本不像企业家，就像一个推销员一样。他制造了这个晶体管的收音机，结果后来却成了美国经济霸主地位的一个挑战者那么不仅仅是盛田昭夫，其实80年代的时候从汽车钢铁美国的工业已经面临着日本后来居上这样的一个挑战了。但是真正颠覆美国科技领先 主地位的是什么呢？就是消费电子产品。最开始像索尼这样的公司，其实就是复制美国竞争对手的产品，复制完了之后把价格降下来，价格降下来之后再把质量升上去，结果最后就发现美国人发明的东西，日本产品质量更好，价格更低。但是这个日本人呢，对于自己可以说是非常的妄自菲薄，说什么呢？说我们只是工匠，美国更擅长创新。当时索尼有一位研究总监是谁呢？是一个物理学家，叫做菊池诚。他在接受美国记者采访的时候说我们日本没有天才你们美国呢是有一长串天才，但是为什么日本擅长大规模制造呢？因为你们美国有一长串智力低于正常水平的人。这个话一想，我们觉得有点意思大家在看到今天中国的工程师和美国的工程师，中国的人才和美国的人才的对比的时候也往往会有这样的一个想法，就是美国多天才，但是中国更多的有平庸但是却可以实施计划的这样一批技术不错的工程师。那么在安德森对于美国芯片质量发现问题之后在1979年可以说是有一个颠覆行业的发明，是什么呢？就是索尼推出了随身听这个随身听可以说对于整个后来的音乐行业是一个颠覆式的创新。那么索尼在发明了这个随身听之后在全球的销量是多少呢？可以说在1年之内就达到了4亿台随身听。当时不仅仅是日本的天下，也是历史上最受欢迎的消费品。这样的一个情况就引起了硅谷的不安。其中有一位硅谷的首席执行官叫做桑德斯不是这一位左派的美国政客，而是 AMD 的首席执行官。他就讲到说整个这个芯片行业现在的竞争已经是你死我活了，绝对不可逃避战争。当时美国的芯片行业还有一位大佬叫做斯波克。这个斯波克呢，最开始在仙童当时非常著名的美国芯片公司开始了职业生涯，后来又经营了美国国家半导体公司一个存储芯片的生产商。他就发现说曾经呢，我们是把整个的亚洲芯片组装进行离岸外包，本来是给我们降低成本，但是现在不妙他就讲到说你现在开车去经过通用电气曾经的工厂，已经是空无一人，美国的制造业出了问题。他说现在我们正在与日本开战这不是枪支弹药之战，而是有关于技术生产力的经济大战。但是这个斯波克虽然是看到了日本的威胁，他对于日本之所以成功的原因的分析却并不是这么的公平。他认为我们硅谷的企业是公平竞争，但是日本的这一些芯片存储公司就是知识产权盗窃，同时呢就是政府给他们补贴他有没有依据呢？有一个依据，就是当时有一位叫做程赖纯这样的一个日本人为一个叫做间谍公司格林马这样的地方服务。那么的确他呢是拿着门禁卡进入了飞机制造商经营的秘密工厂，拍摄最新电脑等等等等。那程赖纯供职的这一家日本公司窃取美国工业机密的公司是哪一家呢？好，就是鼎鼎有名的日本公司日立但是这呢其实是一个比较孤立的这样的一个案例，虽然是有一定的证据，完全说当时日本整个的芯片行业就是靠盗窃和间谍起家的，似乎也并不那么公允。 当时呢，其实受到间谍指控的公司啊，还不仅仅是日立，比如三菱东芝都曾经有过这样的法律纠纷现在呢，你去回看当时80年代的《纽约时报》商业版的头版，经常是这个日本公司的员工被逮捕进行间谍活动。另外我们也这个有一说一，虽然进行经济间谍活动是非法的，但是其实在硅谷美国公司之间互相窃取知识产权的活动也是引起了相当多的法律麻烦。美国芯片制造商其实也一直是互相起诉。那比如说这个仙童，我们之前提到过，还有这个德州仪器这个张仲谋曾经供职过的地方，花了几十年的时间就是打官司到底谁发明了集成电路。美国的芯片公司之间互相挖角对方的这个明星工程师去窃取竞争对手的生产流程的机密，其实也是有很多这样的相关的诉讼。虽然当时日本可以说在新闻媒体中被放大了，但是我们就说这样的非法活动在行业内部其实谁都在做，并不仅仅是日本的文化特色。但是刚才我们提到的这个桑德斯和斯波克也说说日本企业不公平，为什么呢？还不仅仅是他们窃取我们的机密，而是他们受到了国内政策的保护。这一点有没有道理呢？的确，日本有一些这个大型的国家企业比如说这个日本电信电话公司 NTT 可以说呢在日本是电信业的一个垄断公司，类似于现在的这个中国移动和中国联通那它呢就是采用政府采购的方法，几乎全部是从日本本土的供应商这里面来买芯片那这一点呢也的确是。另外呢，日本政府是不是对于本国的芯片制造商补贴呢？也的确是。比如日本政府在70几年的时候就有一个叫做超大规模集成电路计划这样的一个研究团体，其中的这个预算呢有超过一半都来自于政府资金有点相当于现在的这个大基金等等等等。但这个问题是什么呢？就是说美国政府自己也是参与支持半导体的。那比如说最开始资助芯片创新这个部门来自什么地方呢？叫做 DARPA DARPA 是什么？是五角大楼的一个部门。所以我们就说这些呢对于日本公司的指责有道理，但是完全说是因为这一些因素让日本超过了美国，其实并不那么的恰宜。但是说到有一点真的是让日本公司可以说有一个先天的政策优势是什么呢？实际上是那个时候的利率。那我们一看20世纪80年代美国要对抗严重的通货膨胀，所以美联储的这个利率是一度达到超过20%，所以信贷成本在美国非常的高。而日本呢，信贷成本可能就是6%、7%，那就是美国的1/3到1/4左右。另外呢，日本的这一些公司那不管是日立也好三菱也好属于大企业集团。那我们知道日本的这个大银行和大企业是有非常非常密切的联系的。美国的贷款机构呢和这个企业之间那更多的没有这样的联系。所以这个日本的这些芯片制造商的确是在银行这里有比较长期的贷款的支持，而且这些贷款呢本身又比较廉价。还有一个是什么呢？就是说美国的这个社会那么没有那么多的储蓄，但是日本当时呢没有很健全的社会安全网，反而是刺激了储蓄。另外呢，日本当时的金融市场并不发达，对于投资对于股票都有严格的这样的一个投资选择。结果日本人没有办法，又想存钱那么又没有股票的选择，怎么办呢？存入银行账户。结果银行的存款非常的丰富，发放贷款利率也比较低，因为现金多嘛。所以我们就看到有廉价的资本，那么日本公司可以说这个在这个我们叫做投资上这个有源之水这一方面的确是比美国的竞争对手走在前列。大家一听这样的一个文化结构，这样的一个资本市场以及大公司之间的联系，所以让我们想到了现在的中国。 当然了，如果说这个存储芯片让日本占了后发之机硅谷还可以接受，真的让硅谷觉得是我们叫做灭顶之灾的是什么呢？就是光刻领域。最开始美国在光刻领域可以说是独步天下，一个著名的光刻设计公司是什么呢？就是 GCA， 现在大家已经没有听说过了但实际上当时是独步天下。但是后来日本公司开始制造自己的步进式的光刻机，著名的尼康等等等等。那尼康大家呢现在还听说到。这个光刻机不一样，为什么？因为精密制造这个技术的要求和存储芯片完全不在一个量级上，所以当时大家发现美国的这个光刻机质量以及数量都被日本后来居上。美国一些分析家认为 GCA 的衰退是日本崛起、美国衰退的最好的证据。而这一种衰退其实不仅仅是在一个领域，从钢铁开始，汽车开始，存储芯片开始，再到精密制造，再到光刻机。那么整个的这样的一个趋势，让当时的美国创业者感到非常的不安。当时有一个非常著名的经济学家叫 Robert Reich 叫做罗伯特赖斯，就讲到说硅谷叫做纸上创业主义。什么呢？就是说的好听，而不是真正的注重技术进步。他也特别注意到，在美国大学里面学科学和工程的学生越来越少。他宣布美国的教育已经失败了。最后的结果是什么呢？到80年代中期，我们看到短短的10年之间，日本的这个尼康的产品的成品率明显已经比美国的当时的佼佼者 GCA 要好很多，而且故障率要低很多。比如有一家企业IBM 大家都知道， IBM 最开始是使用 GCA 的叫做这个光刻机，那我们叫做平均无故障时间是多少呢？75小时。后来是换成了尼康的这个光刻机，这样的平均无故障时间是多少呢？10倍800小时左右。当时很多的美国企业不仅仅是 IBM 就发现美国的这一家光刻机企业GCA 非常的傲慢，销售人员来了之后就像老板一样根本不把顾客看在眼里。但是日本的公司来了，尼康来了非常的谦逊。另外整个这个 GCA 的管理层也出现了非常严重的问题，更多的时间不是去经营企业，而是与华盛顿的政客们往来各种各样的社交。结果就是管理非常的不善甚至有一些高管直接用公司的信用卡买这个豪华轿车等等等等所以这个公司的花钱如流水另外就是质量的确是下降，整个硅谷的文化又出现了大企业式的臃肿这样的一个情况。到20世纪80年代中期后半叶的时候GCA 的收入营收已经是下降了2/3以上，可以说是一代一代的暴跌那么日本的尼康最开始呢可以说是一个小弟根本比不上 GCA， 但是后来却发现现在已经超越了美国的高经济的这样的一个竞争者。那么到底怎么办呢？硅谷这些大佬们还能不能够挽救美国于危难之中呢？当时我们有几个硅谷的大佬，我们提到的桑德斯，我们提到的斯波克，还有著名的诺伊斯在这个 Palo Alto 这样的一个中餐馆里面有了一次聚宴。这个中餐馆叫什么呢？叫做明式中餐馆叫做 Ming's Chinese Restaurant。 我们在硅谷的朋友们可以去探索一下历史，看看在什么地方。他们就想到了说咱们必须得团结起来了3大最大芯片制造商的 CEO 齐聚一堂。当时呢，明式中餐馆是少数的美国的餐厅里面有私人包间的地方。他们就找了一个新的策略，说我们要拯救美国的半导体。怎么拯救呢？不是靠技术创新，而是求援。向谁求援？向华盛顿求援。 这3个人里面呀，口才最好的就是我们刚才提到的桑德斯，他就找到了一点，说当时啊，在80年代的时候，大家最担心的是什么？石油危机。说我们要这样跟华盛顿说啊，日本正在成为半导体领域的沙特阿拉伯啊，半导体就是80年代的原油，谁控制了原油，谁就会控制整个电子行业。73年到79年的这个石油禁运啊，让美国人心有余悸。当时啊，美国的经济因为阿拉伯国家啊削减石油出口啊，主要是惩罚美国支持以色列啊，让美国的经济陷入了长达10年的滞胀。那么不管呢是这个当时的这个卡特总统也好，后来的里根总统也好，还是乔治布什也好啊，可以说呢，在对外战略上，石油都是关键啊。那么这个美国海军啊护送油轮啊在海湾啊，布什和伊拉克开战等等等等，当时是可以说是整个的这个美国新闻的头条，天天都是这样的一个消息。因此桑德斯就到华盛顿说美国你们可以派遣海军来确保这个石油的供应，现在你们也应该动用全部的力量来穿越世界，确保美国的芯片地位。于是这几位首席执行官就一起成立了一个著名的机构，叫什么呢？SIA。 现在大家一听美国半导体行业协会，然有很大的我们叫做政策上的导向，以及政策上的在华府的地位。当时成立这样的一个行业，就是要游说华盛顿支持半导体行业的发展。那么这样一段历史今天大家听起来会觉得有一点似曾相识让大家也想到美国和中国在当前在科技领域的竞争。那么到底美国是如何这个最后呢是战胜日本，日本又是如何陷入失落的10年、20年、30年呢？现在中国又从日本当年的教训里面汲取了怎样的这个我们叫做痛苦历史美国这一次能不能够重新像当年一样重振雄风？未来我们在讲述黄仁勋有关的故事的时候呢，也会把这样的一条政策线索作为一条暗线，为大家分享我们所了解的更多的信息。那么今天在节目中为大家介绍的主要内容是来自于 Chip War 叫做芯片战争这一本书。之前在节目中呢，我们也为大家特别推荐到。好了，以上就是本期节目的全部内容。我们呢也请何明先生来点评如何看待日本后来居上80年代让美国芯片行业可以说是如梦初醒，一觉被打回解放前这样的一段往事。
大家好，谢谢李记博士我觉得这一期的思想新知报是李记博士最近几个星期来讲的最耗时的一个节目不仅是时间很长，而且呢点出了现在美中关系正在进行的某一种科技的竞争也好或者说一种比赛也好一个大的背景，虽然不是直接的讲现在中国的一些现行的政策，或者是这个美国的一些具体的对付中国的措施，而是让我们回顾了当年的日本怎么一夜之间让美国突然之间听醒日本第一这是哈佛大学傅高义教授写的最有名的一本书当时反映了这个美国的恐慌当时我到90年代初期在洛克菲勒去这个 NBC 的楼上去录制这个节目的时候电视节目的时候每一次经过洛克菲勒中心的那个终点的那个池你都会非常的具有感慨当年日本的力量大到可以买下美国但是大家要知道，日本不是一个人口大国既不存在一个所谓的低人群的优势，也不存在一个所谓的好发的这个优势。但是呢，这种日本的这种崛起那么实际上在很大的程度上对今天的中国非常的有这个参考价值。那么对中国的这种发展或者是崛起 过去几十年的这种解释这么多意识形态这么多非常简单化的解释什么北京大学的教授提出来什么好发优势，那好发的优势的国家多了去了，对吧？很多国家都是好发呀它为什么没有变成优势呢？低人群优势那是更大有这个意识形态的色彩。什么叫低人群啊？文革的时候中国的人群更低它怎么会没有变成一个优势其他很多的国家的人群也没有好到哪个地方去那都不是真正发展的这个优势。李奇博士介绍的这个节目实际上在一定程度上反映出来这个日本它是怎么通过一种学习模仿创新最近形成了一个比美国的产品更优质的这个产品。当时的美国对日本的打压没有因为你是我控制的国家我就不打压你因为是盟友我就不打压你，没有因为你是民主国家我就不打压你照样的打压，因为那威胁到美国的地位，那就是国家安全，那就是国家的利益。很可笑的是日本人都知道他们在美国人的眼里就是卡嚓党就是到处拿一个傻瓜相机这里咔嚓一下那里咔嚓一下。我想起在90年代的时候我就参加一些国际的一些博览会一些展览会，你就会发现中国人这个背一个相机，最开始是傻瓜相机，后来有了一些钱以后有了一些比较好的这个相机到处拍现在这种中国人呢比较少见了。实际上中国也经过了这么一个卡萨的过程。实际上工业化的发展就是一个模仿学习那么至于讲到偷窃的问题，那当时也是怀疑这个日本人是不是偷窃也把这个在美国公司的日本员工也进行这个检查甚至司法当局一样的这个监视。所以中国人呢也不要感觉到完全的委屈，也不是说美国人专门针对你是这样。就像今天的美国的这个移民政策大家只是感觉到这么多移民抢了美国人的饭碗。其实100多年以前呢，甚至更早一点时候呢，其实也是一个样子。当时候的美国的报纸上头版头条或者里面出现的各种漫画是丑陋的会给美国带来禁语，会给美国带来黑帮，会给美国带来低劣文化。指的是谁不是印度人，不是中国人，不是拉丁美洲的西班牙裔人，而是意大利人其他的这个欧洲的一些族裔一样的，当时候也是被这个歧视或者是反移民甚至这个美国的警察体系的出现，其中一个原因跟这个反移民或者防止移民都有这个关系。所以有些历史它就是不断的这个重复，这不是因为我们不去看这些历史就以为只是孤立的针对我们，或者是针对这个印度人，或者是针对韩国人，或者是针对新的一些移民，不是这样的。历史它有时候这个人类的这个情感，人类的价值观的变化也不是说上百年就一定会有根本性的突破。好了，我们再回头来讲这个芯片战争。当美国和中国发起芯片战争的时候我的一些朋友，尤其是来自于硅谷，尤其是在美国接受了很好的学习训练的这些博士们科学界的朋友们跟我就进行了一场比较长时间的一个激烈的一个辩论。有一些辩论在这个想点就点周六8点华尔街论坛，大家可能都会看到一些。当然也有一些辩论是我们私下之间进行。在我的这些科技的朋友认为如果美国来禁止中国的这个芯片，那中国的科技就会停滞不前至少呢会加大跟美国的这个差距那么这样一个呢，当时是一个普遍的认知。也正是因此呢，美国政府推动了这一场对芯片的这个限制。而我认为这场芯片限制注定会失败。为什么会失败？因素很多，但是其中有一个很大的因素是大家忽视了。中国是世界上芯片最大的消费市场，也就是说中国的半导体的发展，中国制造业的发展，它不仅仅是对芯片本身有巨大的这个需求， 这种需求它不会因为美国的这个控制就会停止下来。那么中国自己本身虽然有很大的这个缺陷有很大的落后，但是呢，他会想尽一切办法来这个来补上来当时候有一些人，包括这个张忠谋这种受人尊重的科技企业的大佬，都认为中国怎么样。我不认为，我认为芯片战争中国将会突破，而且中国的军事工业不会受这个影响，因为军事工业本来就需要的这个芯片不是那么的这个尖端，而且芯片发展到一定阶段之后真正的尖端的芯片有那么大的一个必要性吗？中国在某种程度上用叠加的芯片就解决了一些问题，当然是不是能够量产，能不能达到美国这种程度，我们现在也不能完全下结论。但是因为用芯片这样一种限制来限制中国半导体通过中国的这个制造业的发展，有一点太天真。而且什么叫科学创新？大家只注意到了在10年10里面，在基础科学方面科学的创新和发明，那美国的力量还是中国还是有很大的这个距离。但是中国有什么？中国有世界上最坚实的这个制造业，而制造业实际上给科学创新带来了一个巨大的这个机会和动力，甚至它的创新是随时都可能会产生。虽然它没有这个理论上的高度或者难度那么具有一种突破性，但是在应用方面它的能力是非常之强。李奇博士在这个节目里面涉及的问题非常之多，层面非常之多故事性也非常强，而且呢也讲到了为什么美国后来出现了这样一个强大的衰退这么一个强大的一个制造业，这么一个强大的先进的这种产业后来慢慢就衰落了不但这个在国际上没有这个像之前80年的那种高品质的竞争力，甚至在很多产品方面落后于这个韩国电视机你也不一定是想到买电视机，对吧？手机你根本就看不出日本有什么手机到互联网这个人工智能，你所有的顶尖的这些东西，甚至包括人工机器人你都看不到。伟大的日本到哪去了？那么一个了不起的工业，怎么一夜之间就不见了这个恰恰是中国现在很多人担心中国会不会重复日本的道路这是一个非常这个有趣的漫长的，而且具有挑战性的这个话题。我很愿意跟这个我们的网友一起分享我的这种思考。有一些事情呢在思想新日报讲了，有一些事情在顶点今天是讲了。为什么中国不会重复日本人的道路，中国也不会重复拉丁美洲的那种陷阱的道路，也不会出现亚洲精英风暴？那是因为中国的经济结构和政治结构所决定的，这可不是什么优势的问题，而是结构性的问题。好了，今天的这个节目比较长这个感谢这个我们的观众欢迎给我们的节目留下你的宝贵的意见，尤其是不同的意见是非常重要的。谢谢大家，再见。
欢迎来到六度解析新闻背后的多维思考，带你洞悉头条背后的世界。在今日华尔街频道的六度解析中，我们将深入探究时事热点，为你揭开新闻背后的真相。在这个信息泛滥、真相难觅的时代，六度解析应运而生。我运用海量数据、人工智能整合以及专家观点，层层剥析每个故事。通过实时背景数据挖掘，确保你获得全面的新闻资讯。然而，我们关注的不仅仅是数据，更重要的是将它们串联起来。我将分析多方视角，揭示隐藏的脉络， 为你提供单一媒体常常忽略的背景信息。无论是政治、经济，还是全球事务，我都将为你带来最具洞察力的分析。试想一下，拥有洞悉全局的能力，做出明智的决策，参与有意义的讨论，这就是六度解析带给你的价值。它不仅仅是新闻分析，更是一种赋能的工具。加入今日华尔街的六度解析，共同探索头条背后的故事。你通往深度理解的旅程，从这里开始。不要只是阅读新闻，要解码新闻，理解新闻，活出新闻。这一切尽在六度解析。立即订阅，不错过任何真知灼见。因为了解真相仅仅是个开始。